Here we are going to apply related rates to expanding and shrinking a cube. So we're working in 3 dimensions looking at a cube. We're given that the volume of a cube decreases at a rate of 0.5 centimeters cubed per second. What is the rate of change in side length when they are 12 centimeters long? So we have 2 numbers that we are given. This first number has decreases with it. It's also called a rate, and it has 2 units. So that's definitely one of the derivatives. We know how fast the volume's changing. How fast does the side length have to be changing? So we want to remember the formula for volume. Since we have a 3-dimensional object, volume is length times width times height. But the special thing about a cube is that they're not rectangular bases, they're actually squares. So the length side is going to be equal to the width side, which is also equal to the height side. So these are all the same number, and when you do s times s times s, that's the same thing as s cubed, right? 2 times 2 times 2, a faster way of writing that is 2 to the 3rd power. So this is going to be s to the 3rd power. So we figured out our equation that relates volume to side length for a cube. It's that the volume equals whatever each side length is cubed. Length times width times height, but they're all the same number. This is what we're going to take the derivative of with respect to time and plug into. So our derivative with respect to time, the derivative of 1v is just going to be 1. But it'll have a dv dt since it's changing with respect to time. So you can choose whether you want to write that 1 in there or not. Then we have the derivative of s to the 3rd power. So we're going to bring down the 3 and subtract 1 for the new power, which will be 2. And then we'll have ds dt. How fast the sides are changing with respect to time. And now we want to figure out how should we plug into this. So we have 2 variables in our original equation. We have v and we have s, and their derivatives would be dv dt as well as ds dt. And we want to figure out the units on these that will help us pick out these numbers. Well, the first thing we were given is that the volume is decreasing at a rate of 0.5 centimeters cubed per second. So looking at that first number, it's talking about volume, so it's not going to be one of the s's. It's either going to be v or dv dt, talking about volume. Well, since it says decreases, it calls it a rate, and it has 2 units, we're going to definitely say that's dv dt, not v. It's decreasing by 0.5 centimeters cubed per second. And decreasing means I want to pay attention here. I'm gonna have to put a negative on that to make it decreasing by 0.5 centimeters cubed. That tells me that the volume is measured in cubic centimeters as well. And then our other number that we're given is that the side lengths are 12 centimeters long. It doesn't say 12 centimeters per second there. It just says centimeters. So it's not a rate of change. It's not going to be the derivative. It's not going to be ds dt. In other words, it's just going to be the regular s. The side lengths are 12 centimeters. That's just a number. It wouldn't be negative ever. The only reason why we're picking between positive or negative is if we're looking at a derivative, whether it's increasing or decreasing. And then ds dt, how it's changing with respect to time, we would say centimeters per second. And that's the question. What's the rate of change in the side lengths? So that's what we're trying to figure out. What is ds dt? Now we're missing v when we go to fill in the numbers that we're given. We're only given 2 numbers, and there are 3 blanks outside of the 1 derivative we were solving for. So we're missing v, but if I check out my derivative, there's no place to plug in v. So I could plug into the original and solve for what v would be. We definitely don't have to because we're not going to end up using it, but just for practice, if you're missing a variable, not a derivative, you're always missing a derivative, that's what you're solving for, missing a variable, plug in to the original. We don't need to know what the volume is for this one, but there are problems where you're not given a variable, and when you go to take the derivative, you need that variable because you have a place where you need to plug in for it. So we're going to plug into the original equation, which is that V is equal to whatever S is cubed. So for ours, it's 12 centimeters cubed. So I'm going to grab my calculator and do 12 to the third power and see that the volume would be 1,728 cubic centimeters. 1728 centimeters cubed. So now let's actually start plugging in what we have here. We're going to solve for ds dt. So I'm going to plug in what dv dt is from over there. It's negative 0.5 centimeters cubed per second. We have 3, and then we have whatever s is squared. Well, the current side length is 12 centimeters getting squared. And we're trying to figure out what ds dt is. How are the side lengths changing? So I need to remember PEMDAS. I'm not going to do 3 times 12 and then square it. I'm going to do 12 squared first, or if you plug it all into a graphing calculator, it does no order of operations if you plug it in exactly like this. But if you are not using graphing calculator, do 12 squared first, then multiply by 3. Exponents before multiplication will tell you that this is 432 times ds dt. So the last thing I have to do to get ds dt on one side by itself is just divide by 432. So negative 0.5 divided by 432. It's obviously going to be a really tiny decimal, and I can reduce that by hitting math enter on a graphing calculator. I'm getting negative 1 over 864, and this is going to be, I'm looking back here, what is ds dt measured in? Sides are in centimeters, the time is in seconds, so this is going to be centimeters per second. This really tiny number, it's like 0.001 centimeters per second for ds dt. Which makes sense, the volume's not decreasing by very much. So we would say as the volume decreases by 0.5 centimeters cubed per second, right? We don't say decreases by a negative because two negatives cancel out with each other. We would say the volume decreases by 0.5 cubic centimeters per second. It's only decreasing by a really small amount, so the side lengths are doing what? Increasing or decreasing? Well, our answer was negative. That was a good thing. I would assume the side lengths are also decreasing. That's what's making the volume decrease. So as the volume decreases by 0.5 centimeters cubed per second, the side lengths decrease by, and you could use that fraction for an exact answer, negative 1 over 864, or I might just round it, decreasing by about 0.001 cubic centimeters per second. It's okay to use the fraction. I just think the decimal looks a little bit better. And what's the only error in that sentence? Happens sometimes. We want to say the derivative we're given. We were definitely decreasing by 0.5 centimeters cubed per second. The side lengths were decreasing by, and then just double check your units. Side lengths should be decreasing by centimeters per second. So they don't necessarily have the same units. In fact, for this one, they don't. Side length is in centimeters, and then because you have side times side times side, the volume is in cubic centimeters. So just be super careful, double check your sentence, double check your units, and now it looks good to go.